let's see what do we mean by the transpose and the trace of a matrix. These two things are also two elementary operations that we perform on a matrix. First of all, the transpose of a matrix. Now folks, this is a very, very easy concept. Let's read the theoretical part of what it's saying. It says, as A is a n by n matrix with elements Aij. Now let's remind ourselves, the I represent the number of rows, the J the number of columns. Then the transpose of A, and how do we write it? We write it with A with a little t in the the superscript of the matrix A, so capital T. That will be an n by m matrix. Now look at what happened here. To form the n by n matrix, we swapped these two around. That was an m by n. We now have an n by m matrix. And what else is going to happen? Well, look at this. With entries, this new matrix, A transpose, have entries Aj, where the initial one had Aij. So it seems that the J and the I also interchanged in that matrix. Okay, so yes, it's right. What happened? The rows in the first matrix became the columns of the second matrix. Or the columns in the first matrix became the rows in the second matrix. So all we're doing is we're interchanging rows and columns. There's a matrix, a 3 by 4 matrix, which is going to become a 4 by 3 matrix if we interchange the rows and the columns. And that matrix is called the transpose of matrix A. Now let's see, there's the first column, or the first row in the first matrix is the first column in the second matrix. Or, as I said, we could think about this as the first column here becoming the first row in the transposed matrix. So really all that it takes, or that a transposed matrix does, is it interchanges rows and columns. Okay, so let's have a look. What is the trace of a matrix? Another very basic and elementary idea. For us, it's not really that elementary. We are coming to come across, if you study linear algebra further in applications in various fields of study, the trace of the matrix becomes rather important. But we're just going to look at the concept and how it is formed. So the trace of an n by n matrix, first of all, you can see it has to be then a square matrix, is defined by the sum of the elements on the main diagonal. Now that's easy. If we just look at the main diagonal in the square matrix and we add the entries on that main diagonal, we have the trace of the matrix. Okay, so how do we write it algebraically? Well, we can write it as the sum of all the entries I, this is for matrix A, where I starts at 1 and finishes at n. Okay, so if it's a 5 by 5 matrix, A1 1 plus A2 2 plus A3 3 plus A4 4 plus A5 5. That's all you have to do to get to the trace of the matrix. Okay, so Aij or Aii denotes the entry in row I and column I for the matrix I. Okay, in square matrices, what can we say about the trace? Well, A and B are the two square matrices we're going to look at, and it's true that, now remember, this is how we write the trace of A. So the trace of A is the same as the trace of the transposed matrix A. Now we'll talk about why now. The trace of the sum of two matrices is the same as the sum of the two traces of each of these matrices separately. So you can work out the trace for matrix A, work out the trace for matrix B, add the two together, it gives you the trace of the sum of the two matrices. Then another property, the scalar multiple of A, the trace of that matrix is the same as the scalar multiple multiplied by the trace of the matrix. Now remember what a scalar multiple is. It's just each entry in the matrix is multiplied by the same number, the scalar 4, whatever the case might be, 4, 5, 6. You multiply each of the entries with the same number. Now here the trace, now remember these are square matrices. So the trace of matrix AB here is going to be the same as the trace of the matrix formed by multiplying B with A. So first you multiply A with B, you multiply B with A, then you get the traces, and you'll see the traces are the same. Now why are these properties true? Folks, the key to that lies in the fact that we're working with a square matrix, number one. And number two, we're talking about the entries on the main diagonal of each of these matrices. Now if you add two matrices, whether you add them A plus B or B plus A, the entries on the diagonal is the same. If you do a scalar multiplication of the matrix A and you work out the trace of that, it's going to be the same as working out the trace of A, because the diagonal entries remain the same. That's this beautiful symmetry in that matrix. Okay, and the same then for the third property. Now you're asking me, what is the trace used for, folks? Now the answer to that is huge. If you're very interested in that, I would suggest you Google that question and read the entries that are there online from people in the industry where the trace is used. Okay, but for our purposes, we are going to look at minor things that we can do with a trace. Now there's one example. Calculate the trace of this matrix. Now remember, to find the trace, you find the sum of the diagonal entries of the matrix. Okay, so we find the sum of the diagonal entries, which mean 1 plus 11 plus 3 plus 1 plus 14. Okay, now you can see if you work out the transpose of this matrix, it is a 5 by 5, then those entries remain the same. Let's just go to that transpose video that I had here. Look at the entries. Oh, this was a 3 by 4. So folks, it's not going to help us. Let's stick to what we're doing here. Okay, so if we add them, then we get the trace of B. It's the sum of all those entries, which is 462. There's a nice interesting way to look at it. I give you the trace of the matrix as 23 and I ask you to find n. So you've got to know that you've got to add those entries together, equate it to 23, clean it up a little bit, and then you'll find the value of n. N can be plus or minus 4. Okay, folks, that is the transpose and the trace of a matrix. Two very easy concepts. The transpose, very important because we are going to use that in our work. Please, if you learned something, like the video, share it, and also subscribe to my channel.